Hello, in this video we will explain a classification model using an algorithm called adaptive linear neurons or Adaline in Python. So Adaline is also a very simple neural, for training classification, and this part in the figure can be seen as a neuron because it takes in odd features then with the weights and the bias which we want to estimate, right? So this times multiplication together and a summation with a sigma for odd samples and with odd features we are interested in, then using a linear function. Although in Adaline, the linear function is called identity function, so it is actually the same as the result of this sigma. So it is actually is nothing, just we can see that it is equal to this net input. This is called net input. Then this result will be compared with the observation of y. Here y is in the classification is 0 or 1. So this is a linear function result with the net input. So this difference will be made as an error. Then based on this error will be updated with the weights and bias with predefined epoch or until it is converged. So this is the training part before this vertical line. So when all this is finished, then the parameters are estimated and model training is finished. Then we will also use a threshold function. Usually this is like a unit function. For example, the net input larger than 0 will be 1 and less than 0 will be 0, like this. So this is only for the prediction part. So this is the training part and this is the prediction part. And the key points in each machine learning algorithm is the optimization for training the parameter, training the model and get the parameters. And in Adaline, it uses gradient descent type of optimization methods to minimize the loss function. So this is the loss function. Or this is optimization objective function. And inside this sigma, we will see I for odd observation. And Z is the net input. Net input means the result of the summation of the multiplication between features of each observation and its corresponding weights parameters, right? And plus bias. So this is the net input and sigma represents the activation function. So here we use a linear or identity function. So this is sigma Zi equals Zi, right? So we have seen shown before. So sigma Zi actually equals Zi. So this is net input. So yi each observation's class label 0 or 1. So minus this net input, this is error for one observation. Then we take this square and sigma for all observations. So this is the loss function, then divided by n. So and 2. This part is only used for the optimization technique. So the key part is this for the error. And loss function with respect to W and B. W is the weights and B is bias. Weights is maybe has the same dimension as how many features we have. So next we will make partial derivative of this loss function with respect to each weight parameter. So here J represent the jth parameter. For example, we have 3 features in model, so there are 3 weights. And the result of this partial derivative is like this. So this sigma, inside the sigma is 2 parts. The first part is the observation case label 0 or 1 minus this net input's activation function. Although we have shown that in Adaline, this actually equals Zi equals net input is the weights multiplied with the feature, then sum together for all these weights and all these products between each weight and each feature. So this difference then times this feature value for this observation. So this j corresponds to this j, right? Then sum together for all the observations and divided by n times 2. Here use a negative because it will be in the opposite direction of the gradient. Gradient is a derivative of this loss function with respect to this parameter. So this is for each weight derivative. And for the BS, it's easier because need not times this feature. Only the sigma of each observed value minus each net input's activate function. Then divided by n and times 2 and with negative. So we got these 2 kinds of partial derivative, and we can update the weights and BS using this formula. So here is the learning rate, eta. It's a very small number. Sorry, I have to correct this negative is from the derivative, but this negative means the opposite direction from gradient. So here we use negative, then times learning rate, then times this derivative, then update each parameter. This is delta, then for each run we will update with the delta parameter. So this is the framework of this Adaline algorithm. So next we show example to classify iris dataset in Python using this machine learning algorithm. We will go to the similar code as the last video for perception, and we just skip part of perception because we have shown this in the last video. Because this video we will use Adaline. So first we will load the data from this website. Then this data frame, the last 6 observations, you can see this data frame has about 150 observations and 5 variables. And the first 4 is for sepal length, sepal width, petal length, and petal width. And the last column, or last variable, is for the label. There are 3 kinds of iris label, and this is one kind of, because the first 50 and the second 50 and the last 50 has 3 kinds of label. And we can also show the data. This scatter plot between 2, we just take 2 features. You can see this group together for the 2 kinds of label. Only 2 label, 2 classes, and with 2 features. So we just skip the perception part, and here we will come back later for this decision regions function. So first we go to Adaline gradient descent. We set up a class because there are several methods for this class. So we have to set up a class. In the parameter eta is a float number for the learning rate between 0 and 1, and iteration for the integer for the epoch, and the random state of the integer, because we will use this for the seed for the random number generation. And the attributes w underscore b underscore loss underscore, this for the weights, this is array is when the array, right? Yeah. And this is scalar, only one number. And the loss feature list, because we will put the results of loss, each epoch's loss in this list. So if we set a 25 epoch for the training, then the list will contain in the end 25 elements. So first in the class we will define the initial function. Then self, eta, and iteration and the random state with initial value. So these three attributes defined in the initial value. So initial function. So we set underscore for w, b, and the loss with underscore because these three attributes are not come with initial function. Then the fit is for the training. Fit method is for the training. So here x is for the independent variable or for the feature data, and y for the label. So x is array-like shape with n examples, observations, and n features. So here we will use 2 features and 100 examples because only 2 classes. So here the shape is 100 rows and 2 columns, and the y is 100 elements for one scalar, one-dimensional array. Then we set a random number generation object using random state function with the initial random state number. Then we also set the initial value for weights parameter. So using this random number generation with a normal distribution with location 0 and scale 0.01, and with the shape is for the second axis of the shape of x. So this second axis has 2 elements, right? Because the first shape is for the observation for the row, and the second axis is for the column. So column has 2 features. So this means the size has 2, right? So we set up 2 parameters for the weight, and BS only for one number. Then the loss in an empty list. So next is the training process. We set an iteration number, so with the range from 1 to this iteration number. Then for each training epoch, we set a net input. So here net input is a function defined later, defined outside of this method. So we will look at it later. So first we calculate the net input of these input features. Then output is the activation function of net input, and activation also defined later. The errors is y minus output. So here very clear. So here the y is a column 100 number, right? And output here is also a column 100 number because we use activate function. So these two difference is also 100 number, right? Then update the weights. Update the weights for this run. So equals eta times 2 times input features transpose, then dot errors. Why we use transpose? Because X shape is 100 row, 2 columns. So we transpose as two rows, 100 columns. Then the result, this is a matrix multiplication, and the results will be 2 row, 1 column. So this is same as 2 numbers, right? So because weight is a 2 number, so we actually update with these 2 numbers, then divided by shape 0 is 100 rows. So here is 100 for the mean. So it's very quite easy to understand. We just update this weight because weight is a 2 number. Update this 2 number with this is also a 2 number, right? And BS is updated with a 1 number. So it's quite easy, right? Then loss is from the error, this is 100 number. 100 number take square, also 100 number, but we take the mean function. It will be 1 number, right? Then this 1 number will be this iteration's loss. And we append this loss inside this loss list for this iteration. So quite simple for this training process. So here is the net input, is the multiplication, also the matrix multiplication with the X input feature times this value for the parameter and the plus BS. So the result is, you can see that this is 100 row, 2 columns, and this is 2 columns, 2 rows, 1 columns. So the result will be 100 rows, 1 column, right? So the net input output is a 100 number. And activation actually will return X. So this is same as the input for the net input. So the activation function will result 100 number in our example. So you can see the net input and activation used here. Net input activation function. So another is predict. Although we will predict not belongs to this algorithm for the training. It is only activation function with the net input. Then this number, if larger than 0, the result will be 1. Otherwise, it will be 0. This is for the result of the classification. So we just run this for class definition. Run this for class definition. And next we will train 2 modules with different eta. So the first eta is 0, 1. And the second is very small, 0.001. And the first is 15 iteration, second also 15 iteration, and we put them in 2 subplots. So in the subplot definition, the first this line for the training fit, then show the results for each epoch's error, and this second model for the training and show this result for each epoch. We'll see how it is going. So the result you can see, it's very strange. The error will be very large and the error will be very straight. So comes this abnormal because we have not scale X features, because different features have different scale, right? Have different scale. So we have to scale them in the same scale. So here we use a standard normalization. Normalization, each feature with 0, mean, and standard deviation 1. So we do this together. Then we train again. Very quick. And here we will show decision region. So this decision region function also can use for most of machine learning. We have shown this in the last video for perception. Here we explain again. This is called a plot decision region. So what this means for this function? So here we set marker and the colors. So here maybe you have 5 classes at most. And we also used a map called CMap from this packages, this function. And how many Y labels, then how many map with the colors, right? Quite clear. Then we set X and Y, X1 and X2. Here, because this plot for the classification region, decision region, is only for the 2 features. Because more than 2 features we cannot plot in one figure, right? So only for the 2 features. So X1 is the first feature and X2 is the second feature. And we get the minimum and the maximum value for these features and the -1 and the +1. So from this map, we use mesh grid. So the mesh grid function will get a matrix. So this matrix with the rows for X1 and choose for the X1 how many X1 and columns for how many X2. And this represents a very, very small dense point on this map because we set the resolution, right? Resolution very small. The solution will be defined later, but this is a very small number. So you can see mesh grid will return a very, very small dense area with each point. Then for each point, the millions of points in this map, we will use the module. Here, classifier is the trained module. In the trained module. So for each machine learning, we have trained modules. We can use this classifier to predict, use the prediction function for each point. So each point from this mesh grid, we will use a level. Level function is to transform this matrix to each one-dimensional line. Because we cannot get the predictor from matrix point directly, right? Because what we can do is only for point get X and X1 and X2 pair. So this is just to get X1 and X2 pair. Then we train model, then we predict the label based on this point. So this is also point, right? X1 and X2. But this is X1 and X2 put on this map. Map is a 2-dimensional, right? So we done this job and then plot this label with different figure and color on this mesh grid map. So this task of job will show what is the predicted label on this map. So usually for linear model, we'll show a map with a straight line divided by 2 colors. Then second job in this function decision region is to put opposite value on this map. So here we get X and Y for the first feature and the second feature, then put each real opposite value with different color and label on this map. So why we do this? Because we want to see opposite of the value match the predicted theoretical region, right? So we run this and show the results of Adaline. So we first run this. So this decision region function has been created, and we go back because we have trained on these scaled features, right? We have trained. So next we can use plot decision region. Then with this X and Y and classification with Adaline GD we have trained. So this is the decision region for the red is for the second class, and for the blue first class, and this point are the real observed points. You can see all the observed points stay at the correct for the region from this model. So this area means the model will define this region, and opposite of the value stay correct in the region. So in other words, the model trained these points 100% correct, right? And we can also show the last training loss results in the plot. So this is normal figure fault loss, one step, one epoch loss. So here is converged, right? Almost about 10 epoch. So we use a 25. So about 10 epoch, the loss has been minimized. So this is the main job of the Adaline with a single neuron, and the key point is Adaline use all observations in one epoch. So we sum all the errors together for all the features for all the observed values in one epoch. Then based on this and compared with the observed value, right? So this is the error for one epoch. Include all the information from all the features and all the samples. Then based on this error, we update weights and bias for one iteration. Thanks for watching.